Welcome to Physics Clinic at the Red Rose Academy. Today, we are going to see electrochemistry. We are going to master the heart of the chapter. Okay. So, by the end of this video, you will know exactly how it works and how to calculate its voltage and how to write its shorthand notation for your exam. So, stay along with me with your paper, notebook, pen, and everything. So, take a note. It's very important for your exam. So, right now, I'm going to explain you about how the galvanic cell is working. So, you must know the working of galvanic cell. Okay. So, before we get into this particular galvanic cell, you must know before we build a battery, we need to understand the underlying chemistry. It's all based on a spontaneous redox reaction. That is both reduction and oxidation. Then we've already learned about all these stuffs in uh, class grade 11. Okay. So if you drop a piece of solid zinc, okay, into a blue copper sulfate solution, a natural reaction happens. So zinc loses electron, that's oxidation. You know, removal of electron, losing of electron refers to an oxidation and dissolves into the solution. Meanwhile, copper ions in the solution grab those electrons, that is reduction, and deposit as solid copper metal. So reduction means addition of electron. This you have already learnt in your grade 11. Because the zinc and copper are touching, the electrons jump directly from the zinc atoms to the copper ions. Energy is released. Okay, but it's completely wasted as heat. To generate electricity, we need to force those electrons to travel through a wire instead. You know, the flow of electrons results in the current. Okay, so and to do that, we have to separate the two reactions into half cells. Okay, so right now we are going to see that one is oxidation, another one is reduction. This is very important. So, what is the oxidation? It occurs at the anode. So, for just keep this as a mnemonic, okay? So, anox. So, this just a mnemonic I just told you. So, it is a mnemonic and anode oxidation. So at cathode reduction takes place. So red cat like that. So just a mnemonic. Okay, I'm just kidding. Okay. So and then the species loses electrons, results in an increasing in oxidation state. That you know. So one solid metal, it becomes actually aqueous by losing electron. Same way, here the species gains electron. That means the aqueous metal, it gains electron and becomes solid. So that's what here. So we'll see now. And I told you about, so this one we'll talk about. So this anatomy of a galvanic cell we'll see. Okay, let's build a classic galvanic cell. Specifically, we can take two beakers, two separate beakers, okay, like this. Two separate beakers. In the left beaker, we place a zinc strip, okay, into a zinc sulfate solution. Got it? So, zinc sulfate solution, it becomes zinc 2 plus. Okay, zinc 2 plus. Okay, this is our anode. Okay, and in the right beaker, we can take copper strip, okay, copper strip into a copper sulfate solution. Okay, so it becomes copper 2 plus ions. This is our cathode. Got it? So how do you remember which is which? Just use the acronym. Okay, I taught you know anode oxidation, cathode reduction. So anox red cat. Okay, so anode is where oxidation happens. Here what happens? Zinc solid becomes zinc ion and it releases 2 electron. Now this electron is connected through the wire. Okay, so the electron is transferred through the wire. Okay, now the two electrodes are connected through the wire. So zinc solid. So what is happening here? At anode, zinc solid, it gives zinc 2 plus ions, aqueous plus 2 electron. Okay, then this 2 electron is transmitted through this wire and it is, attracted towards the cathode. So what will happen here? What is there? Already copper 2 plus ion is there. So this copper 2 plus aqueous now accepts electron. Here reduction takes place, addition of electron, and gives copper solid. Okay. We connect the two metal strips with the conducting wire we saw. Okay, so this and all very important. This is the main point. So here only you can able to measure and take the current. Okay, and the voltmeter immediately. So and then you can see electrons start flowing through the wire from the anode to the cathode. That is zinc electrode to the copper electrode. But wait, there is a problem. As electrons leave the left beaker, it builds up a positive charge because of excess zinc 2 plus ions. Right up. So, as soon as the electron leaves the left beaker, it builds up a positive charge, right? Because of excess zinc 2 plus ions. So, the right beaker builds up a negative charge because copper 2 plus ions are leaving the solution. So the reaction will, I can say it is in a split second due to charge buildup. So the reaction will, it takes place like this. To fix this, we introduce the salt bridge. Okay. So here it will be the salt bridge. It was not indicated here. I'll explain you. So this is salt bridge. You must know the purpose of salt bridge. Okay, that's what I explained this. Okay, if you want to know again, you can rewind the video, and then you just take a note. Okay, pass and then take a note of all these things. Okay, it's a U-shaped tube filled with an inert electrolyte like KCl, KNO3, okay, like that. Okay, so it allows anions. So KCl or KNO3 you are taking in a salt bridge. It allows anions to migrate to the anode, okay, anode side, and cations to migrate to the cathode side. So maintaining electrical neutrality without letting the solutions mix. Now the circuit is complete and the electricity flows continually. Okay, wow. So in your exams, drawing two beakers and a salt bridge takes too long. Chemists use a shortened language called cell notation. Okay, so the golden rule here is very simple. I'll teach you now. Always write the anode on the left, cathode on the right. Think alphabetical, right? A first, A before C, like that you can take. Anode, left side, cathode, right side. So let's write it out for ourselves. Shall we? Okay. Start with the solid anode. Zinc sulfate, zinc solid. Start it with, okay, the solid anode. Draw a single vertical line. Okay, like this. Okay. Kids, students, are you with me? Okay. So listen carefully and take a notes. Draw a single vertical line to represent a phase boundary. It is a phase boundary. I can say everything is given in your NCRT book. So followed by the aqueous ion, zinc 2 plus. Okay. Got it? Is it clear for you? Then draw a double vertical line like this. Double vertical line to represent the salt bridge. Okay. Write the aqueous cathode ion, Cu2 plus. Got it? Draw another single phase boundary line like this and finish with the solid cathode, copper solid. So this is how you have to do. Put it all together and it looks like this. Okay. So I'll explain you like zinc solid, single vertical line, and then zinc 2 plus aqueous. Then for a salt bridge, double vertical line, and copper 2 plus, this is aqueous, here aqueous, then single vertical line, copper solid. Got it? So this is the way you can write the cell. Okay, instead of drawing all these beakers and all, it is the simplest way, and it will not consume your exam timing. Okay, so you must know, students, how to write. Okay, so left side anode, right side cathode. Okay, so calculating standard cell potential, that is very important. So I taught you about this salt bridge, role of the salt bridge, and it maintains electroneutrality. Okay. Okay. So I'll explain you this. Okay. Standard cell potential is very important. Okay. Finally, how do we predict how much voltage the cell will produce under standard conditions? We calculate that standard cell potential. Okay. That is known as standard cell potential. Standard cell potential. Okay, and it is represented by like this standard cell. Okay, so the formula, but in this you have to understand what is E cell. E cell is equal to standard electrode potential, that is equal to E cathode, sorry, okay, minus E anode. Okay, E cathode minus E anode. So I'll explain you the like standard reduction potentials. Both values must be written as the standard electrode potentials. Okay. So suppose if you are given, let's look at a typical problem based on this. So say for example, you are given, okay, copper 2 plus copper. This you know what is it? Positive 0.34 volt, and this is zinc 2 plus, and zinc, okay, it is equal to negative 0.76 volt. It is given. Since copper is at the cathode, reduction has to takes place. And zinc is at the anode, oxidation take place. Okay. So you know all these things, reduction, oxidation. Okay. Then we plug them directly into our formula. How we can, so this is E cell is equal to standard cell potential is equal to E cathode minus E anode. So what is the standard cell potential for this? What is E cathode? This one is reduction. This is cathode, right? So 0.34, 0.34 volt plus, right? And then negative of negative anode potential. So 0.76 volt. So what is the total? 0.34 plus 0.76. So it is 110, right? So plus 1.10 volt. So this is the standard potential. So a positive E cell means the reaction is spontaneous. If the E cell is positive, the reaction is spontaneous. Okay, and will successfully generate a current of 1.10 volt. Okay, this is very, very important. And that is how the chemical energy is converted cleanly into the electrical power. Okay. Okay, let's quickly recap the essentials for your boards. Oxidation happens at the anode. Got it? And what else? Then negative terminal, that is in galvanic cells. Reduction takes place at the cathode, positive terminal. Salt bridge maintains electrically neutrality. Always calculate your cell voltage using cathode minus anode. Okay. In our next lesson, we'll look at what happens when conditions are in standard using the famous Nernst equation. If you find this breakdown helpful, hit that like button, subscribe for more high yield chemistry breakdowns, and drop any questions or any doubts you have in the comments below. See you next time. Thank you.